Yes, so dear student, I Rakesh Jain from Gambia University. Today I am going to teach you about the Stephen Boltzmann law and Newton's law of cooling, which we will derive the formula of this Newton's law of cooling from Stephen Boltzmann law. After the completion of this lecture, you will be able to understand that how the difference of the temperature of body of any body and the surrounding temperature is proportional to the heat emission rate, and how we can say that the perfect black body radiated emission is proportional to the fourth power of the temperature. So after the completion of this lecture, you will able to understand that the modes of transmission of heat actually related with the Stephen Boltzmann law and Newton's law of cooling. So just we begin just our journey from this MS Paint file. First of all, just see this MS Paint file. Yes. So here I just write down the name of the topic, Stephen Boltzmann law. So what is the meaning of Stephen Boltzmann law? The Stephen Boltzmann law states that Stephen Boltzmann law. Stephen Boltzmann law states that the heat radiated per unit time per unit area from a black body is proportional to fourth power of the absolute temperature of the body. So Stephen Boltzmann law states that the heat radiated per unit time per unit area from a black body is actually proportional to the fourth power of the absolute temperature of the body. This is the statement of Stephen Boltzmann law. Okay. So what is the meaning of this one? Let's suppose we have a black body whose emitted radiation, that is known as the per unit time per unit area, the heat radiated per unit time per unit area from a black body is, let's suppose, indicated by E. Let's suppose it is indicated by E. So E is my emitted radiation, we can say. We can say E as emitted radiation, or we can say it is heat radiated per unit time per unit area from a black body. So let's suppose the emitted radiation of the black body, or we can say heat radiated per unit time per unit area from a black body is denoted by E. And let's suppose T is my absolute temperature of that black body. That T is my absolute temperature of the black body. Then according to the Stephen Boltzmann, this is absolute temperature of the absolute temperature of the black body. And according to the Stephen Boltzmann law, actually this E is proportional to the fourth power of temperature. So the Stephen Boltzmann law, in the formula we can say E is equal to, E is proportional to the fourth power of temperature. This one is the indication of Stephen Boltzmann law. We know that whenever the proportional sign we just remove, there should be one constant, and here the constant is Stephen Boltzmann constant. So sigma T raised to the power 4 is the E is equal to, that is emitted radiation or radiated emission. The radiated emission is proportional, is equal to the Stephen Boltzmann constant, multiplied by fourth power of the absolute temperature of that black body. Here the meaning of sigma is the Stephen Boltzmann constant. Here sigma is Boltzmann constant. Boltzmann constant. It is given as is actually equal to 5.67 multiplied by 10 to power minus 8. 10 to power minus 8. So it is known as Stephen Boltzmann law. It is known as Stephen Boltzmann law. If we want to write down the unit, it is watt per meter square per meter square Kelvin is raised to the power 4. Okay, so this is Stephen Boltzmann law. This is Stephen Boltzmann law. Now the second one, this is Stephen Boltzmann law. So we have to just see the statement of the Stephen Boltzmann law. That is, the emitted radiation of a black body is actually proportional to the fourth power of the black body, fourth power of the temperature of that black body. So is proportional to T raised to the power 4. Whenever we just remove the proportionality sign, there should be some constant, and this constant is your Boltzmann constant sigma. So E is equal to sigma T raised to the power 4, and which is actually equal to 5.67 multiplied by 10 to the power minus 8 W per meter square K raised to the power 4, watt per meter square K Kelvin raised to the power 4. So this is Stephen Boltzmann. Now, what is the statement of the Newton's law of cooling? The Newton's law of cooling states that the heat emission rate, the rate by which the heat radiated from a body, okay, this is known as heat emission rate. The rate by which the rate of the radiated emission from a body is known as heat emission rate. So the heat emission rate is actually proportional to the difference of absolute temperature of the body and surrounding temperature. So the Newton's law of cooling, I just write down the statement here. Newton's law of cooling said that so Newton's law of cooling said that the heat emission rate is proportional to the difference between heat emission rate means the rate by which heat is radiated or emitted from a body, any body, okay, not related with only the black body. Okay, so Newton's law of cooling states that the heat emission rate is proportional to the difference between absolute temperature of body and surrounding temperature. The surrounding temperature means the temperature of surrounding, okay, room temperature we can say. This is known as Newton's law of cooling. So Newton's law of cooling states that the heat emission rate, actually the heat emission rate is denoted by dQ upon dt. The heat emission rate is actually denoted by dQ upon dt. So dQ upon dt is actually, the dQ upon dt is actually equal to, is proportional to T minus T0. Is proportional to T minus T0. So I just write down this statement, this thing here. Just move a little bit to the upper side. Okay. So the Newton's law of cooling states that the heat emission rate, that is denoted by dQ by dt. dQ upon dt. This is known as heat emission rate. This is known as heat emission rate. The rate by which the heat is radiated or emitted from a body. So dQ upon dt is proportional to, let T is the temperature of the body and T0 is the room temperature, or we can say temperature of surrounding. So dq upon dt is proportional to T minus T0 is the statement of Newton's law of cooling. Yes. So this one is the second thing, Newton's law of cooling. Now we have to derive that dq upon dt is actually proportional to T minus T0 with the help of Stephen Boltzmann law. That's why it is written that derive the formula from the Stephen Boltzmann law. Derive the formula from the Stephen Boltzmann law. So we just start this thing. Okay. So now we will derive derive the Newton's cooling law from Stephen Boltzmann law. So I just save this file and just see the new page. Which is the topic name is derivation of Newton's cooling law from Stephen Boltzmann. So derivation of the Newton's cooling law from Stephen Boltzmann law, we have to derive this thing. Now we will start. Before starting, first of all, just write down both of those laws in formula basis so that it will be easy for you to derive those laws. Okay. So I just write down from the previous slide. I know that what is the Stephen Boltzmann law. What is the Stephen Boltzmann law? The Stephen Boltzmann law states that the radiated from a body, that is a black body, is proportional to fourth power of the temperature. So from this, I just find out that actually E is equal to Boltzmann constant sigma multiplied by T raised to the power 4, where T is the temperature of that body, that is a black body. Okay. And what is the Newton's law of cooling? Newton's law of cooling states that the heat emission rate, that is actually given as dq upon dt. Heat emission rate is given as dq upon dt is equal to is proportional to the difference between the absolute temperature of the body and temperature of the surrounding. Okay. So we have to derive this thing. We have to derive this equation with the help of this. Okay. So we begin our journey from the Stephen Boltzmann law and see what will happen. Okay. So let's suppose. So to derive this, let the absolute temperature of the body is T. Let the absolute temperature of body is T. At the absolute temperature of body is T, and the temperature of room, or we can say surrounding, temperature of surrounding is denoted by, let's suppose, T0. Okay, T0. And this T minus T0 is known as the difference of temperature. So the difference of those two, absolute temperature and temperature of the body, let's suppose this difference of temperature is denoted by del T. So I just want to say that let's suppose T minus this T0 is actually equal to the difference of the absolute temperature and the room temperature or the surrounding temperature is, let's suppose, denoted by del T. So this heat emission rate is also, which is the heat emission rate is given as the heat emission rate, that is denoted by dq upon dt, is actually given as this heat emission rate, that is dq divided by dt. This heat emission rate is given as E dash E. E dash E. This heat emission rate is actually given as E dash E, where A is the cross-sectional area and E dash is the emitted radiations. That is actually the difference of emitted radiations from the body and emitted radiation from the dead body. We know that E is equal to E dash is what? E dash is here the meaning of E dash is that is emitted radiation, the perfect emitted radiations. It is known as perfect emitted radiations, we can say. Perfect or exact, we can say. Emitted radiation. The perfect or exact emitted radiation. E dash. Okay. So E dash is actually equal to E minus E0. E minus E0. Where the meaning of E is, I just write down here. In this circuit. Where this E is the emitted radiation from a black body, because I take the example of black body here. And this emitted radiation due to the temperature of surrounding, that is E0, that is E sigma T0 raised to the power 4. So when I put the temperature as temperature of the perfect black body, I just denoted it by T raised to the power 4. That's why E is equal to sigma T raised to the power 4. And when I put the temperature as temperature of the surrounding, then it is E0, let's suppose, and E0 is equal to sigma T0 raised to the power 4. So this E dash is equal to E minus E0. So we can say that this heat emission rate, that is dq upon dt, is equal to E dash, that is E minus E0. So sigma is common, T raised to the power 4 minus T0 raised to the power 4 multiplied by E. Once again, I am showing you here how it will happen. E dash is equal to E minus E0. So what is E? E is sigma T raised to the power 4. So I just write down as sigma T raised to the power 4 at place of E. At place of E. And at place of E0, I just write down sigma T0 raised to the power 4. So this E dash is actually equal to sigma is common from both of these. Sigma is common, and in bracket I will find T raised to the power 4 minus T0 raised to the power 4. Okay. So I just copy this thing and put there, which I have already been brought, but once again I will write down it there. So this heat emission rate is equal to sigma T raised to the power 4 minus T0 raised to the power 4 and multiply by. So this dq upon dt is equal to, this dq upon dt is equal to, now see very carefully, dq upon dt, that is heat emission rate, is equal to, we can write down sigma and A together, and then in bracket, that is T raised to the power 4. And we have already been seen in equation number 1 that T minus T0 is equal to del T. It means T is what? T is equal to, actually equal to T0 plus del T. T is equal to T0 plus del T. From this equation, we can say T is equal to T0 plus del T. From this equation number 1, that is the difference of the temperature, T minus T0, absolute temperature, and the temperature of the surrounding is equal to del T. It means what is T? This minus T0 when will move towards the right hand side, it will be plus T0, and it will add with del T. So at the place of T raised to the power 4, at the place of T raised to the power 4, I just remove this simple bracket sign into. So this sigma is together. Now at place of T raised to the power 4, I can write down T0 plus del T raised to the power 4. Minus T0 raised to the power 4. Okay. So this T0 power 4 as it is, this A is as it is, this sigma is as it is. At the place of only this t, I just put t0 plus del t. So now we have to derive. So I just remove from the left hand side these things that will be available in decoding. So you will be see later on. Okay. So we have to prove this one. So I am here. So, yes. So I am here. So dq upon dt is equal to sigma I in bracket t0 plus del t raised to the power 4 minus t0 raised to the power 4. From this first part t0 plus del t, I just put common t0. So it will be moved externally. So it is sigma A. When I take this t0 as a common, then this will be t0 will be at outside because power is 4. Because this power is 4, that's why t raised to the power 4 will be moved externally. And at the place of t0, 1 will be there, and plus del t upon t0 will be there, which together have the power of 4. Minus t0 raised to the power 4. So t0 raised to the power 4 is common, then 1 plus del t divided by t0 minus t0 raised to the power 4. So now I just clear this right hand side so that I will explain it to you. So now dq upon dt is equal to, so this dq upon dt is equal to, I just take this t0 outside. So t0 raised to the power 4 is common from both this side, both this case, from this first and from this second. t0 raised to the power 4 will be common. And in bracket you will have 1 plus del t upon t0 raised to the power 4 minus 1 as it is. From the first case, first side, this is first, and then minus 1 will be there. Minus 1 is why? Because t0 4 we will take as outside. You know the mathematical rule, that is, I just write down here that for, let's suppose I have 1 plus x upon y raised to the power, and if this del t upon t0, or we can say x upon y, is very less, and if it is have a power, that is large power, then it will be equal to 1 plus nx upon y. This is the basic rule. When there will be negligible effect of this x upon y, when there will be any negligible effect of this x upon y, then we can ignore this and directly multiply by the power. So this is a rule that 1 plus x upon y raised to the power n. Or instead of x upon y, if you have any lower value 1 plus x only, and it consists to the power of anything, let's suppose n, then we can write down that one as 1 plus nx if the effect of that x is very less. So by using that rule, we can write down as, if you have any confusion related to this rule, we will talk about this thing after the completion of the lecture. If you have any query, you can ask me after the completion of this lecture. So sigma a t raised to the power 4, then 1 plus this 4 will be multiplied by del t upon t0. From where it comes from, if you don't know about this mathematical rule, you can ask me after the completion of this thing. So minus 1. So what will happen? Now this 1 to 1 will be cancelled out. Now this 1 to 1 will be cancelled out because both are of opposite side. And we will have, I just remove this left hand side. So we will be able to understand this thing. Now this dq upon dt is equal to, this dq upon dt is equal to sigma a t0 raised to the power 4, sigma a T0 raised to the power 4 multiplied by 4 del T upon T0. See very carefully. Now this T0 raised to the power 4 will be decreased to T0 cube because of this T0 at the beginning. Now this T0 will be cancelled out. From this T0 raised to the power 4, instead of power of 4, it will be 3. I will write down this in the next step. So dq upon dt will be equal to, see very carefully. So this dq upon dt will be equal to 4, I just write down 4 sigma, this one 4 sigma, then A, 4 sigma A T0 cube, that is room temperature or surrounding temperature cube, and delta. So see very carefully. This 4 is a constant. This 4 is a constant. This sigma is a constant, that is of 5.867 multiplied by 10 to the power minus 8. Okay. A, cross sectional area. Area is always a constant thing. Surrounding temperature, that is of fixed value. The room temperature, like 23 degrees Celsius, 32 degrees Celsius, they are the particular room temperature. So this is also a constant. Only del T is a variable thing, because del T, so we can say dq upon dt is proportional to, if we know that whenever proportional will be removed, then some constant will become, so this constant is the value of this, that is 4 sigma A T0 cube. The multiplication of all those 4 terms will also a constant, so that is proportional to del T. So dq upon dt is proportional to del T. So when I remove this proportional again and I write down equal sign, then what will come as a constant? The 4 sigma A T0 raised to the power cube. Okay. So dq upon dt is proportional to del T. And from the first equation we notice that the difference of the body temperature, and I again write down here, just see carefully for what was the first equation. So the difference of the temperature of the body and the surrounding is equal to del T. So at the place of this del T, I can write down this thing. So now see. So from this I can write down as, dq upon dt is proportional to, at the place of del T, I can write down from equation number 1, that was T minus T0. And what is this? This is Newton's cooling law. So we prove that, where I wrote this Newton's cooling law here, see this one. This was Newton's cooling law. We start our journey from the Stephen Boltzmann law. We do all the necessary modifications according to the basic rules, according to the basic formula, and finally we will find out what we derive. Finally, we derive that dq upon dt, that is heat emission rate, is proportional to the difference of the temperature between the body absolute temperature and surrounding temperature. So that is your Stephen Boltzmann, that is your Newton's cooling law, which is derived from the Stephen Boltzmann. Okay. So in the lab practical, when you will see that how the temperature difference is in the lab. Whenever you will do the practical, that what kind of things you will notice there. So this is the perfect completion of this topic, that is derivation of Newton's cooling law from Stephen Boltzmann law. Okay, so let's remove this one and see this one. When you will do the lab practical on this Newton's cooling law, what is the thing you will notice? That you just take any utensil You just put water over there. How to do the practical of Newton's cooling law in lab? That you just put the temperature water. Just heat up that water for some time. Just heat up that water for some time. Okay. And when you will heat up some water for some time, then definitely the water will be before that before heat up. The water was cold. Now it will be hot. Now just put a thermometer over there. Now just put a thermometer over there that will show you the temperature. So let's suppose this is a thermometer. पुष्कर आवाज आ रही मेरी? एक बार अनम्यूट होके बोलो मेरे से। पुष्कर, निशा आवाज आ रही मेरी?
यस सर।
यस सर।
हाँ सुनो पुष्कर, बेटा ये अभी रिकॉर्डिंग चली, मुझे मालूम है एकदम से लाइट चली गई थी तो एकदम से कट हो गया था वो। तो ये मैं अभी तक जितना बोल रहा हूँ ये भी रिकॉर्ड होके आएगा, इसको आपको कट करना है, फिर आगे से अभी जो मैं बताने वाला हूँ उसके साथ में ऐड करना है। काम कर लोगे ना पुष्कर?
ओके सर, कर देंगे।
हाँ अभी रिकॉर्डिंग जैसी क्लास खत्म होगी मेरे पास 10 मिनट में आ जाएगी, उसके बाद मैं तेरे को मेल करूँगा तो कट करके मेरे को भेज देना और कल मुझे बता भी देना कैसे।
ओके सर।
ठीक है यार, अपना टाइमिंग।
ओके सर।
नाउ सी, so let you have this thermometer in that water which is actually heater. So you just notice the temperature, and you just notice the time period. You let the small t show you the time period and the capital T show you the temperature. So after some time, the time, let's suppose at the T1 time the temperature is capital T1, at the time T2 the temperature is capital T2, at the time T3 the temperature is capital T3. So continuously you will do 10 to 20 readings will be, you just take. Okay, then the water will be, the temperature will be continuously decreases. So you will find out a graph. Let's suppose here there is a difference of temperature of T minus T0. Okay, the room temperature is fixed. Maybe 23 degrees Celsius or 32 degrees Celsius, whatever the temperature at that time. Okay, you just notice when you will just begin the practical at the starting time, you just notice that temperature, and at each answer this T is your T1, T2, T3, T4, T5, T6. Okay, so what kind of table you will find out for this graph? First is the serial number. So you will write down from 1 to 20 readings. So 1 to 20 you will find out. You just write down the temperature which you notice at different time, that is T1, T2, T3, T4, T1, T2, T3 up to T20, whatever the value is. And T0 is totally free, totally constant, So just write down T minus T0. For each reading of this T's, that is T1, subtract it from T0 and write down the reading here. So you will find out different readings, till 20 readings you will take. Okay. Then write down here the small t value, that is your temperature value, that is your time value. Okay, so at what time you find out this this t value, you just write down t. Okay, so we notice that when time will be increases, definitely the temperature difference will be continuously decreases. Okay, so this kind of curve you will find out after the completion of that practical. After the completion of that practical, you will find out this kind of. So I hope you understand about this Stephen Boltzmann law, Newton's law of cooling, and derivation of Newton's law of cooling from the Stephen Boltzmann law, and you understand the very simple practical how to perform, how to find out the graph between the temperature increase and the decrease of the temperature difference. The time increase and the difference of the temperature will be decreases. Okay, so I hope you understand this. So let me see just one or two objective questions on this. I just remove this one and see these objective questions. Okay. Which one is the correct statement of? Which one is the correct representation of Stephen Boltzmann? Okay, which one is the correct representation of Stephen Boltzmann? And you have four different options. One is the heat, where the symbols have their usual meanings. Okay, so E, that is heat emission, the radiated emissions or emitted radiations, is equal to sigma T raised to the power 4 multiplied by cross sectional area E. E is equal to sigma T raised to the power 4. T is equal to T minus T0 or dq upon dt is proportional to T minus T0. Can it? Yes, you can write down your answer in the text message. Okay, yes, answer is B. Very good. The answer is correct. That is very simple. We just studied a few minutes ago that E is equal to sigma. This one is the correct answer. No. This one is correct answer. No. This one is correct answer. No. The answer is that radiated emission is proportional to the fourth power of the temperature of that black body, and when we will remove the proportional sign, Boltzmann constant will become, that is denoted by sigma. That's why E is equal to sigma T raised to the power 4 is the correct representation of the Stephen Boltzmann. And instead of this, if I write down that which one is the correct representations of Newton's law of cooling, let's write down as Newton's law. So you understand Newton's law of cooling. Then what will be my answer? Just write down message box. Yes, my answer is D. Definitely it will be D, because Newton's law of cooling states that the heat emission rate is proportional to the difference of the absolute temperature, the difference between the absolute temperature and temperature of surrounding. So these are certain kind of numericals we see, certain kind of objective questions we see. So I hope you understand about the Stephen Boltzmann law, Newton's law of cooling, and the derivation of Newton's law of cooling from the Stephen Boltzmann law. So Rakesh Jain from the Gyanware University wants to say you thanks for watching the video. Thank you very much. If you have any query, you can type in the message. Thank you very much.